Right, okay, we're going to look at conservation of energy leading to changes of energy in terms of transformations more than anything else. Okay, so we start off with the basic idea of energy. Now you should know from GCSE that energy cannot be lost or created. It's just simply transformed or transformed into a different type. So you do all kinds of simple demonstrations of that. So we have kinetic energy of my hand moving, turning into sound energy and a little bit of heat when my hand warms up, okay, when I smack it against things. So that's just a really simple example of an energy transformation there. So energy cannot be lost or created, it must be conserved. Energy is always conserved. If you're ever asked a question, what's conserved? Energy is always the thing that's conserved. So that leads us on to our next scenario. So we'll look at something that falls as the most simple example. So as something falls to the ground, it starts to change the type of energy it has. It starts with a type of energy called GPE. Now you will be familiar with GPE from GCSE, or you should be, and that changes into kinetic energy, KE. And that is all to do with the idea that as it falls, the GPE reduces and the kinetic energy increases. And so the change in GPE is equal to the change in kinetic energy, K. And that's nice, we can just make an assumption about this. So for example, if it had 1,000 joules at the top here, then as it gets to the bottom, then it would transfer that kinetic energy at this point into 1,000 joules of kinetic energy at the very bottom of the fall. Okay? So it's that transfer between. And as you can imagine the same thing as you throw the ball upwards. As you throw a ball upwards, it starts with that amount of kinetic energy, and by the time it reaches the top point, as high as it can get, it will have transferred that all into gravitational potential energy. So no issues there. So what the real difficulty becomes is when we start looking at this equation in terms of, or this relationship in terms of the equations that represent them. So in this case we've got GPE. Now you should hopefully remember from GPE what the equation for GPE is, mgh. And that change in mgh is going to be equal to a change in kinetic energy, which kinetic energy is a half mv squared. Pay close attention to these equations because you are not given them. Okay, you are not given them. So you do need to know this equation. It needs to be on the forefront of your mind when you're talking about any kind of energy transfers, especially kinetic energy. Now, the nice thing about this is it actually throws up a nice relationship between equations we've already used in the past, and hopefully you might see a very nice similarity here. So if I can do some algebra around this, well, we're saying we're talking about the same mass. So we can divide both sides by m, and that will get rid of m. Let's not worry about the change sign too much. And that's going to leave us with gh equals half v squared. And if I rearrange this further, I can essentially allow me to work out at a certain height above the ground in the gravitational field due to gravity, which is g 9.81. We can work out a velocity if we do the algebra right. So get rid of the half, so times both sides by 2, so 2gh is equal to v squared. And then finally get rid of the square, we square root both sides, so square root of 2gh is equal to v. And that v is the velocity in the case of the ball being dropped. Is the velocity at this point here. This is the ground. The very bottom of the drop is when all the GPE is changed into KE, that velocity is what we're getting. The height in this case is the height that it was dropped from to the ground from where it was raised up from. So this is a really nice equation to use, and funnily enough, it's not too dissimilar to one that you've seen before. You may remember an equation, one of my favourites, Suvat equations, v squared equals u squared plus 2as. Well, what we have here in a situation where something is being dropped, u would be 0. So we get rid of that, we end up with v squared equals 2as, which means that v is equal to the square root of 2as. And if you look very carefully there, 2gh, 2as, well, g is the acceleration, a is acceleration, height is the displacement from its original position, s is displacement. So, and v is obviously the velocity we're looking at, and square root is fit there as well. So it's all exactly the same. So what happens next is we need to look at a more difficult example. Okay, so in the next video we'll look at an example of using this, and we'll build on it into some of the previous material that you might have watched as well.